All right, so we are continuing our 3.1 notes. We need a calculator for today's notes because we're going to be talking about the natural base number e. So for a lot of applications, the convenient choice for a base is the irrational number e. And e is about 2.718, but it does continue on 281, 281, 281. It's irrational because this is not really a repeating decimal because of the 7. And this number is found, this ratio is found in a lot of different applications. It's called the natural number because you can find this ratio occurring in nature, and we will use it mostly for applications of exponential growth, decay, and compound interest. Okay, so if we have a function that's f of x equals e to the x, that's called the natural exponential function. So still an exponential function. The base number is about 2.718. So you can sketch this graph without a calculator because remember, for exponential graphs, we have a horizontal asymptote of y equals 0. That's easy to sketch in. Convenient numbers to plug in are when you plug in 0, e to the 0 is still 1. And when you plug in 1, you get the base number e to the first. And remember, e is about 2.718, but I really only need to think 2.7 when I'm plotting this. So if you plot a point somewhere between 2 and 3, I will be happy. I'm not going to say that that's not at 2.7. And then this has the curve of an exponential function where it's increasing continuously. If I want to graph e to the negative x, I still have a horizontal asymptote at y equals 0. Having a negative in the exponent, remember, that's just a y-axis reflection of this graph. So I'm just reversing, or I'm just multiplying the x-coordinates by negative. So I'm still going to have 0, 1. But instead of 1e, I'm going to have negative 1e, because that would be e to the positive first. And again, e is about 2.7, so that's how I will plot that. So negative 1, 2.7, 0, 1. Again, this should just look like a y-axis reflection of the other value. And that's all that I really need to sketch for these graphs. There are 2 compound interest formulas that you need to have memorized because we use them so often. So the first one is used if you have n, let's see, actually I want to do this. If the interest on the account is collected n times annually. So what that means is you've got money sitting in, let's say, a savings account, and interest might grow on it once a year, or they might collect interest twice a year, or 4 times a year, or every month, or every day. So n would be however many times per year you're doing that. To outline some things, A is the final balance after a certain number of years. P is the principal amount. How much did you start off with in the account? R is the interest rate. It'll say the annual interest rate, and you're going to write that as a decimal. So if the interest rate is 2%, you're going to put in 0.02. N is the number of compoundings. We already said that. And T is the time in years. All right. And then if instead of interest being collected every day, every month, twice a year, 4 times a year, whatever, if the interest is collected continuously, you can't assign an n to that. That would be n approaches infinity. Interest collected continuously. So that's more than every day. That's, continuously throughout the day, every day for the year. Then we use this. So P is still the same, A is still the same, P is still the same, R is the same, T is the same. E is the base number. So I just want to make a note. E is not a variable. So when you're typing this into your calculator, you're using the E key, which is about 2.718, et cetera, et cetera, et cetera. All right, so how do we do these problems? So we need a calculator, first of all. And let's go ahead and just label things. So it says a total of $9,000 is invested. So that's the principal amount that you're starting with. at an annual interest rate of 2.5%. So R is going to be 0.025. Remember, you just divide this by 100 or move the decimal 2 places to the left. T is 5 years. Find the balance after 5 years if the interest is compounded semi-annually. So how many times a year would semi-annually be? Twice. Let's go through and list this first. Quarterly, how many times would quarterly be? 4 times a year. There are 4 quarters in a year. Daily, how many days in a year? We're not worrying about leap years or any of that stuff. So 365 days a year. Continuously, there is no N for that. So you use A equals PE to the RT. All right, so let's set up our formula. So again, you need to have this memorized. It will be A is equal to 9,000 times 1 plus 0.025 over N, which is 2, raised to the NT, so 2 times 5. Let's go ahead and calculate that. So 9,000 times 1 plus 0.025 divided by 2, raising that to the 10th power, 2 times 5. We're talking about dollars here, so instead of rounding to 3 places, we'll round to 2, round to the nearest cent. So 10,190. The balance is about 10,190.44. All right. And then when you do this, the formula just keeps staying the same. The only thing that changes is N. So I'm still talking about investing $9,000. Now it's 1 plus 0.025 over 4, collecting interest 4 times a year. Raise that to the 4 times 5 power. So I just have to make some adjustments up here. I can go up here and grab this equation and say instead of dividing by 2, I'm going to divide by 4. And instead of having an exponent to the 10th, 4 times 5 is now 20th. It makes sense that I have a slightly higher amount because I collect interest 4 times a year instead of twice. So if you're getting 2.5% on top of what you already have 4 times throughout the year instead of just twice. So that's 10,194.37. Okay, for this next one, I'm not going to write out the formula. I'm just going to change my values here. So now I want to type in 3 digits. If I just start typing in 365, it might write over some of this. So you can go second delete. See how it says insert up there? Type in your 3 and your 6, and then you don't want to keep inserting, so just arrow off of it. It's not a big deal to type over the other stuff and just retype it, but whatever. I do not know what 365 times 5 is off the top of my head, but I can just do that math in here. If your calculator does not show you this math type, then you need to make sure that you put parentheses around your exponent. Like if you see the caret here still, then you need to have parentheses around the exponent. 10,198.29. Oops, yeah, 0.29. So that makes sense. That's even more, not much, but still more than I had previously. And then continuously. So continuously, remember, we're not using an N value. We're using this formula. So this is going to be A equals 9,000 times E to the 0.025 times 5. There are some interesting proofs, by the way. You can find them on YouTube, I'm sure, of like where these formulas come from. So if you're curious about that, feel free to investigate it. This should be slightly higher, but very close to the daily value. So it's just a few cents more. So 10,198 point, was it 33? No, 0.34. Make sure that you're rounding correctly. You don't want to lose silly points on the AP test just because of rounding. All right, and then here's another example of, this is not an interest rate, so you're given this formula here, but this says let Y represent the mass in grams of radioactive strontium, whose half-life is about 29 years. The quantity of strontium present after T years is given by this. So see what they've done here? This is kind of good to know, just you can sort of build the formula here. Where did this 10 come from? This is going to come down to an initial mass, which we'll figure out in a second. But when you do half-life, it'll always be half to the T divided by whatever the half-life is. That means that it'll take 29 years for, if you have 100 grams, It'll take 29 years for it to get down to 50 grams. All right, so what characteristic in this equation makes this a decreasing function, or why is this exponential decay? We get that question in multiple choice a lot, and this is kind of an easy one to answer as soon as you realize what you're looking for. When the base number is smaller than 1, you're going to have a decreasing function. We looked at that with our exponential graphs before. So y is decreasing because the base number, the base, is less than 1. 1/2 is less than 1. If this said 10 to the 1.5, 10 times 1.5 to the t over 29, that would be a 1.5 would be an exponential growth. What's the initial mass? So this just means anytime they say initial, that means when time is 0, like before things started. So what is y of 0? That'd be 10 times 1/2 to the 0 power. We know anything to the 0 is 1. So 10, and then I label y in grams. So we started with 10 grams of radioactive strontium. How much of the initial mass is present after 80 years? That's a t value. So this is asking us to put an input of 80 and find the output. So that would be 10 times 1/2 to the 80 divided by 29 power. So off to our calculators here. 10 times 0.5 to the 80 divided by 29. Again, if you don't have this math type in here, if you see the caret, you need to put parentheses around 80 over 29. Round to 3 places again, now that we're back to not money. So 1.478 is about equal to 1.478, and this is measured in grams. Now, we will talk about how to solve exponential equations, but for this one, how many years will it take for 0.3 grams to be present? So we're saying set your equation equal to 0.3 and solve. So I don't want you to solve this algebraically. I mean, I guess if you know how, you can, but I want you to solve by graphing. That's an important skill that we need for our AP exam. The reason people avoid solving by graphing is because they can't always see the graph. So use the previous question to help you figure out the window. Let's go to y equals. Let's type in, it doesn't matter in what order. I've got 0.3 here. And then 10 times 0.5 raised to the x over 29 power. Now, what do I want my window to be? So when I plugged in 80, I was at 1.478. So it's definitely got to be something bigger than 80, but I could even start at 80. And then I just have to do a little bit of guessing and checking. So I don't know, is 200 far enough to go out? I will have to see. So I'm going to say 80 to 200, and then I'm going to zoom fit. And if I can see the intersection, then I'm good. See, I can see the intersection. That's great. I might have done 80 to 300 in my first on my answer key, so that's fine too. And then I'm just going to find the intersection point. So my answer is 146.708. So t is about equal to 146.708. Time is measured in years. That's about how long it will take to get the 10 grams down to 0.3 grams. Again, in a few days, I will show you how to solve this algebraically. But even after you learn how to solve it algebraically, on a calculator part of our AP test is finishing in time, right? So why solve algebraically if you have the option to solve graphically? You want to get fluent in that. It's also important for calculus next year. All right, that's it for today's notes.